Hello and welcome to the Thermochemistry Heats of Formation podcast. In this podcast, I'm going to explain how we can use heats of formation and how we can calculate heats of formation. All right, so let's take a look at a problem here. In the problem, we're given a table of heats of formation. Now, in your notes, oops, that's not very dark. In your notes, I gave you a heats of formation table that was a lot longer than this, but obviously we won't be able to see if I put the whole thing on here, so I shortened it just to the ones that we're going to need. You can use the longer list for ones that you'll need for reactions that don't contain just these three things. All right, so the problem asks us to determine the heat of reaction, so the amount of heat that's produced for the combustion of butane. Okay, so first step, we have to write the chemical reaction. So any combustion reaction, we have a hydrocarbon, that's going to be our butane, and it burns in the presence of oxygen gas. That reaction arrow is only going one way because we're definitely not reforming those. And we're going to end up getting CO2 plus H2O. Now we've got to balance this. So in order to balance this, we're going to end up putting a... Alright, so I've balanced this. Now when I initially balanced this, this was actually 5, this was 2, and this was 9 halves. The problem with this is you really don't want to have to deal with any halves, even though that's acceptable in a combustion reaction. So what I did, I just took all of these and multiplied by 2, and that's how I got 2, 9, 4, and 10. Alright, so I'm going to take those away so they don't confuse us. Alright, so the equation for heats of formation, to use it to solve for a reaction, is the overall heat of reaction, the delta H of the reaction, is equal to the sum, this sign means sum, if you don't remember from math, from the delta H for the products minus the delta H for the reactants. And if you think about this in terms of an energy diagram, so if you kind of go back to an energy diagram, it really makes sense because what you're doing is you're taking the difference between your products down here and your reactants up here, and this is going to be your delta H value. Okay, and so you're doing the same thing up here, it's just you're doing it in terms of an equation instead of reading it off of a chart. So I'm going to erase that just so we have room. Served its purpose. Okay, so now we have to actually plug in the values. So our delta H for a reaction is going to equal. Okay, so I'm going to put brackets around all of the products just to keep us nice and organized. So our first product is CO2, and we have 4 of them. So we'll do 4 times, okay, well, CO2 is negative 393.5, and this is the sum, which means to add up. So the next one is going to be our water, and look here, we have 10 waters, and each water is this value, negative 241.8. Okay, oops, it's taking a lot of room. And then minus our reactants. Now if we look over here, we have 2 reactants, but one of them's not listed on our charts, and that's oxygen. Elements in their elemental state, so oxygen is diatomic in its elemental state, they don't have a heat of formation. They're considered 0. They're defined as 0. So the oxygen will not be included in our heats of formation calculation. That's different when you watch the podcast for the bond energies because they will be included in there because diatomic elements do have bonds, but in heats of formation they do not. Alright, so the only one we need to worry about is the butane, and we have 2 of them, and each one is that value. So we'll do 2 times negative 125. Gonna run out of room. 1.6. Okay. All right. So now it's just a matter of calculating. So what I suggest that you do is you calculate all of this one, get a value, and all of this one and get a value, and then subtract the two just to keep your numbers organized. Okay, so when I put everything into the calculator, I got my delta H for the reaction. Sometimes they'll call this a delta H of combustion since this is combustion reaction. That's the same thing. Negative 374.1. And one of the things that you'll notice is this value up here is in kilojoules per mole. So that means that your units will be kilojoules per mole. Okay, so that would be my final answer. The next problem is going to be a little bit different, and we're actually going to need this table and these values. Here we're going to come back to them because we're going to need them on the next page. All right, so it says the heat of combustion for propane, which is C3H8, is negative 2220 kilojoules per mole. By the way, why would that make sense? Why would this give you less energy per mole than this, than the butane? Well, if you think about it, butane has more bonds, right? So for every mole of butane, you have an extra carbon-carbon bond, and you have 2 extra carbon-hydrogen bonds. So that's going to release more energy. The longer your hydrocarbon chain, that's a hydrocarbon, the more energy is going to be released in your reaction. Okay, so if we take a look at this, it says set up the shortcut calculation for the delta H. The only reason why this is sometimes called the shortcut calculation is because the other ways to do it would take a lot longer. One would be using bond energies. One could be doing the heats of formation based on delta Hess's law, and they can take a long time. Since we know a lot of the values for this, it'll be easy to solve backwards for it. Okay, so we'll calculate the delta heat of formation for this. So in this case, we're not looking for the delta H for the reaction. The delta H for the reaction is actually given to us. That's this value right here. What we actually want to solve for is this value that we would have used here, okay? And so if we, if we want to solve for this before we can actually even set this up, and let me erase this, we first got to write the chemical reaction. So let's take a look and write this chemical reaction. So you've got propane plus oxygen. Let me leave room to balance it. Reaction there is definitely only going one way. CO2 plus H2O. So 4, 3, 6, and 4. So that's 5. Okay, so this one we don't need to multiply by 2 because we get a whole number in front of the oxygen. So now let's set up our equation. Okay. The delta H for the reaction is going to be equal the sum of the delta H for the products. So that's going to be our carbon dioxide and our water, which we know the values for because they're given to us here and here. So we'll come back and get those in just a second. Minus the delta H for our reactants. And if we remember from the previous screen, this will not be included in the reactants. So the only thing that's the reactants is the propane, which is what we want to solve for. So this will be our unknown value. All right, so let's plug all of these in. Okay, so delta H for reaction is given to us as negative 2220. Okay, I'm getting that directly from right here, the problem up above. Equals, okay, well, we've got 3, oops, hold on a second, let's fix that. We've got 3, and each one of the CO2s, if we look at the previous screen, is negative 0.5 plus we've got 4 waters. And so that's negative. Let's look at the value. 241.8 minus, okay, and this is going to be our x. So I'm just going to put this down as x. You could leave it as the sum of whatever delta h. That's what we want to solve for. Okay, so now it's just a matter of adding these values up and solving for x. Okay, so the value that you get for the x, which is defined as the heat of formation for the C3H8, is equal to negative 72.3 kilojoules per mole. Okay, and so this would be your final answer. And this would make sense because if you look here, oops, I went back too far. This is a much bigger value, right? Because this has more bonds. So as it forms, it would release more energy. It's actually interesting, though, in combustion reactions, we always think of the energy really being in the hydrocarbon, but it's really the potential for the hydrocarbon to form CO2 and to form water that actually releases all of the energy, because when these bonds form, they're incredibly stable, and then that's actually what, in the end, generates all of the energy that we use in combustion reactions.